Hello and welcome to Stupid Muted. Hello and welcome to another exciting math lesson with me, Mr. Lin. So we're going to dive right into it. This is 3.2, Analyze Graphs of Polynomial Functions. So here we go. So first, face, get smaller. Oh, come back here, face. There we go. So again, section 3.2, Analyze Graphs of Polynomial Functions. So in the last lesson we had talked about higher degree of polynomials and some of their characteristics. So now we're going to learn more about how to analyze some of those things. So as always, to spark your learning, think about a woodcrafter is crafting an open top box from a rectangular piece of wood. The woodmaker will make the cuts marked, then place the sides of the top of the edges of the base. The corner cutouts will be discarded. So if you can kind of imagine, this part right here of the wood would be the side, and they would just fold up. So as always, what is a mathematical question you can ask about this situation? So you could talk about, there's the bell, but you could talk about things like, how do I maximize the volume of this box? How do I maximize the length and the width? Does that go together? What if I need a certain area of the box? So all of these things we can kind of work with, but it would require a higher degree polynomial. So again, some further information. So the piece of wood is ½ an inch thick. So that's going to matter as how much volume is taken up by the sides. The cuts are made the same way each corner. The longer sides are placed on the base first. So these will all help us with figuring out how to cut the box. So it'll help us answer things like, what is the maximum volume of box that we can make out of this situation? All right, so task 1, identify key features of graphs. So, and there we are. So here, let's say we have our parent function of x cubed. So remember a quick down and dirty of that graph. Oops. So it's going to come up like that and go down like that. But what we can do is we can replace one of those factors of x with a linear factor like x minus 1. So that would just be a polynomial function, which is, here is our definition right there. But what that does is it turns the graph into something like this. So again, this is just by turning, actually this is by turning a couple of them. So you will see up here is our graph. We'll move it up a little bit so you can see it. So simply by changing some of the x's to x plus 1 squared and then x minus 1, we now have a very different looking graph. So some things to point out. So first of all, you can talk about like a minimum and maximum. So we've got our global maximum, otherwise known as an absolute maximum. I prefer absolute maximum, but that's just me. So the absolute maximum is going to be this part right here. It's literally just the highest number that it goes up to. So the global maximum is just the highest number that it goes up to. So on the opposite, what you can't see right here is the global minimum. That is again going to be the lowest number that it goes down to. So when I'm talking about high numbers or low numbers, I'm using the y-axis right here. So just so we're on the same page. There's some other things you can talk about. You can talk about things like where does it cross the x-axis. So we've got an x-intercept here. We've got an x-intercept here. But you'll notice that there are two different types of intercepts. So either way, algebraically, in those 2 points, no, not x, f of x is going to equal 0. So that tells us where that point is, but it doesn't tell us what that graph is doing at that point. However, if it crosses the x-intercept, then we're going to call it crosses the x-intercept. So we're going to call it a cross. Or the other way is if it is tangent. So for those of you who don't remember geometry, tangent is just this guy right here. Notice how it's not crossing, or it's not crossing the x-axis, but it is touching it and then going back down. So those are some of the characteristics that we're going to be looking for. You can also talk about what's called local minimums and local maximums. So, those words kind of just mean what you would think they would mean. So like right here, this is a local maximum because you'll notice that the graph is coming up. That's the tallest that it gets and it goes back down, at least in this small local area. And then we have a local minimum right here. Again, it's not the global or the absolute minimum, but the graph is coming down or it's decreasing and then it's increasing on the other side of that. So that is the lowest point in this local area. So these are some of the characteristics that we're going to be looking at in this section. So we talked about most of these. So number of distinct factors. So if we look at the graph of x cubed, so there's one factor, again that's x, x, and x. So here there's going to be two factors. You've got x, and you've got x minus 1. And then for this last one, you're going to have three factors. You'll have x, x minus 1, x plus 1. I guess it's something I have to drag. Oh yeah, there it is. So we'll drag this. That's not the right answer. Well, anyway, we'll just talk through it. I don't need to drag to show you. So then you've got your x-intercepts. Again, algebraically, we can find the x-intercepts just by turning f of x into 0, and then we can solve. So very quickly, x squared, obviously x equals 0 is the only time that it touches the x-intercept. So for this next one, x can equal 0 right there, or x can equal 1. So if I set this part equal to 0. And then moving right along, this last one, I can set x equals 0, I can set x minus 1 equals 0, I can set x plus 1 equal to 0. So again, we're going to have x equals 0, positive 1, negative 1. So then when it comes to tangent or cross, that's where we're going to kind of need to look at the graph of each of these functions. So what you can do... Oh no, it's lunchtime. What you can do is just pull out your graphing calculator to kind of solve some of these so you get a feel of what they look like. So I just pulled out my app on my phone, and I'm going to type in x squared parentheses x minus 1 close parenthesis, and I'm going to graph that. Pardon me while I zoom in. So real quick sketch of what I'm looking at. You've got kind of something that comes down, up, and then back down like that. Again, use your graphing calculator so you get a better view of that. But from that, we can, or at least from the graph I'm looking at on my calculator, I can tell you that there is, over here, there is one cross where it crosses the x-axis. It's going to be kind of right there. And there is, so one cross, and there is one tangent. So that's kind of right there. And then we're going to stick with this graph because I have it up on my calculator at this point. So we'll just go down the list. So number of turning points. So I didn't talk about those in the beginning, but turning points is literally just where it is going from increasing to decreasing or decreasing to increasing. Basically, every time where that graph turns is a turning point. So number of turning points, again, I see 1, 2. So turning points is 2. And then on here, it says number of turning points at a global maximum and then at a local maximum. So because my graph kind of looks like that, there's no turning points at either a global or local maximum or minimum, but we've got a local maximum right there and a local maximum right there. And then number of turning points at global minimum at a local minimum. So again, each one of these would be 1. So we would have, let's line it up. We would have 1 at a local max and 1 at a local minimum. So, okay, we can do the rest of these, or the next one. Again, go to your y equals function on your calculator, and I'm just typing in x, open parenthesis, x minus 1, close parenthesis, open parenthesis, x plus 1, and graph. So this one, again, this is a very rough sketch. So I'm looking at something that comes up, goes back down, and then comes up again. So if we go down the column here, so there are 3 distinct factors. I count 1, 2, 3 x-intercepts. That makes sense. Those x-intercepts, let's see here. This first one is a cross. Second one is a cross. Third one is a cross. And again, that's because the graph is going across the x-axis. So I would say all three are crossing the x-axis. Number of turning points. So I see a turning point right here, a turning point right here. So I'm going to stick with two. Two turning points. So then when we go into number of turning points at a global minimum or a global maximum, so again, this one up here is a global maximum. I'm sorry, a local maximum. So there's one local max, and then this one right here is one local minimum. And the reason I say that is because there are values down here in this area that are smaller than this one, and the same up here. There are values up here with this graph that are bigger than this local maximum. So that is why they are local maximums and not global. Okay, so we just went through that chart, and we'll notice a couple of things that are consistent throughout the different types of graphs. So if you examine your table from parts A and B, what seems to determine the number of x-intercepts the graph of a polynomial function has. And so the number of x-intercepts the graph has appears to equal the number of distinct factors a polynomial has. And that kind of makes sense when you have something like, you can set this equal to 0, this equal to 0, and this equal to 0. So that just means that there's going to be 3 x-intercepts. The number of x-intercepts is less than or equal to the degree of the function. And so, again, if we have something like x cubed, there's only one x-intercept, which is x equals 0. But there's definitely no more than 3, something like x plus 1, x minus 1, x plus 2, or something like that. So there would be 3 zeros or x-intercepts for that one. So what observations can be made about the degree of a polynomial function? How is this related to total extrema indicated in the graph? So you can use the degrees, how many degrees of the function, and it can help you determine how many extrema. So that's either a local maximum or a local minimum, and it depends on how many turning points you have. So using a graphing calculator, calculate the graph f of x equals that stuff. So I plug that in. Again, I push the y equals button, and x, open parenthesis, x minus 0.5, close parenthesis, open parenthesis, x minus 1, close parenthesis, open parenthesis, x plus 1, close parenthesis, and graph it. And I'm getting something that kind of looks like this. Now, of course, this is not to scale, but let me zoom out real quick to make sure that that's right. Yeah. So that's, again, not a great drawing, but whatever. It'll get the job done. Do your observations here and in part C hold for this function? So yes, there is an equal to or less amount of zeros, things like that. What observations can be made about how many times a linear factor of a polynomial function in intercept form is repeated, and whether its graph crosses the x-axis at the indicated x-intercept or is tangent at the x-intercept. So let's see here. Let's figure out what they're talking about here. How many times a linear factor of a polynomial function in intercept form is repeated, and whether its graph crosses the x-axis at the indicated x-intercept or is tangent. So here is our function. We're just going to write that down so we can see it later on. X minus 0.5, right? Yeah. X minus 1, and then x plus 1. So we've got this x minus 0.5 right here. So I'm going to zoom in on my graph to see if... Oh, it's hard for me to tell, so we're going to zoom in some more. So what I'm trying to figure out is, does this crossing point right there, is that really 0.5? I mean, it might be. Maybe it's 0, 0. I don't know. So let's zoom in just a little bit more. Yeah, it definitely looks like 0, 0. Oh, but I get it. So this intercept right here is 0.5. So that is still 0, 0, which makes sense because that's our x equals 0. And then we've got this intercept right here, which is at 0.5. So that kind of makes sense. And that is a cross. So it crosses through. And I don't think we actually have any tangents on this graph. So moving right along. As soon as there we go. Let's see here. I think we just did that one. How would a leading coefficient of -1 for each polynomial affect the graph? So just as it always has been, if we throw a negative sign right here, it will be reflected. The whole graph will be reflected around the x-axis. So that kind of makes sense. That's what all the rest of our graphs do. For polynomial functions, which domain is all real numbers. So this is kind of an interesting question. Will the graphs of a cubic function have a global maximum or minimum? Will the graphs of a quartic function have global maximum or minimum? Explain. Can you extend this reasoning to functions to polynomial functions of greater degree? I would say yes. So if you remember, a cubic function looks like this. So this goes on for infinity, this goes down for infinity. So you're never going to have a global maximum or minimum because the function goes on forever. Whereas on the flip side, a cubic function looks kind of like this, kind of like a flattened out parabola. And again, you are going to have a local minimum, a global minimum right there wherever the vertex is. And I would say that that can be extended to all odd functions for this one right here, and all even functions for this one right here. So if you remember, all odd functions, even if it's coming whatever, you're still going to have one part of it going up for infinity, you're going to have one part of it going down for infinity. Whereas the even functions all kind of look like cattywampus parabolas, and so they're always going to have a global maximum or minimum depending on if there's a negative sign in front of it. So I like that. That's a good observation to make. All right, so here we go. All right, so our next task is going to be to sketch the graph of a polynomial function. And of course, they're going to be in intercept form. So a polynomial function's value is 0 at each x-intercept over the interval between two consecutive x-intercepts or beyond any x-intercepts. The function values can be only positive or only negative. Otherwise, the graph would cross or touch the x-axis again. Because intercept form is a product of factors, the sign of the function for any value of x is found by multiplying the signs of the factor for that value of x. The end behavior of a polynomial function, all of that, is determined by the degree of n and the sign of a. A is that number right out front. Use this and the intercept form to, as described above, lets you sketch the polynomial function of graphs. Okay, so real quick before we get started, what in the world did all of that say? Because it's a lot there. So basically, what it's saying is if you have a graph, something like this, you've got your x-intercepts, so what it's saying is that in between these x-intercepts, it can either be only negative or only positive. So in this case, that first interval is only positive in yellow. That other middle one is only negative in green. And then if you go down over here, this is all only negative and only positive. So that makes sense because if we're talking about these x-intercepts, anything above it is positive, anything below it is negative. And if something goes from positive to negative, then it crosses the x-intercept. So it can't do that unless it hits another x-intercept. So it's a fancy way of saying that. And then this end part right here, the end behavior of a polynomial function, can be figured out by looking at a, basically the sign of a, and then remembering that your odd degrees, your odd polynomials look something like that, and then your even polynomials would look something like that. And of course, a negative sign would then just flip them around. So that's basically what it's saying. And then because intercept form is a product of factors, the sign of the function for any value of x is found by multiplying the signs of the factor of the factors for the value of x. And I'll show you that here in a second. So, okay. Let's graph a function. So I'm going to write this one down just so we can see it. So f of x is equal to x plus 4, x minus 2. So it's already factored for us. So as we move down, the first step is to figure out the end behaviors. So the degree of polynomial is 3 because there's 1, 2, 3 x's. So the parent function would be our x cubed, and remember that is something like this. So that means as x approaches negative infinity, f of x is going to approach negative infinity. And then conversely, as it approaches positive infinity, f of x is going to also approach positive infinity. And of course, if there's a negative sign in front of it, then those would be reversed. Okay, so that's all we needed to do there. So we know that the end behaviors of our function. So what does end behavior tell you about the graph? It can tell us whether it's generally increasing or decreasing, things like that. So then it says identify the graph's x-intercepts, use them to define intervals, and create a table to find the sign of the function over each interval. So when it says use the graph's x-intercepts, so an x-intercept is when y equals 0. So we would set this whole thing equal to 0. And I'll work this one out long-handed, but this is something where it might save you some time to start trying to see these things. So x minus 2. So if any one of these is 0, any one of these factors is 0, the whole thing would be 0. So here we go. So if x equals 0, the whole thing would be 0. If x plus 4 equals 0, that means minus 4, minus 4. X equals negative 4. Or if x minus 2 equals 0, same thing. Plus 2, x equals positive 2. So then what you can do is you can put them on a number line, and you can get your intervals. So we've got 0, we've got x equals negative 4, and then we've got x equals 2. So we have a couple intervals here. We've got this interval, which we know is decreasing and approaches infinity as it goes further to the left. We've got this interval we need to figure something out about. We've got this interval that we need to figure something out about. And then we've got our other end behavior, which that one increases infinitely. So these are our intervals. So you'll notice that they have them written right up here. So as x is less than 4, in between negative 4 and 0, in between 0 and 2, and then 2 on up. So that's where they got those numbers. They use the factors as x-intercepts to then figure all of that stuff out. So we're going to get rid of all this. Alright, so now they are trying to find the sign, whether the function is positive or negative. So whether it's above or below the x-axis. So the way they do that is you've got your intervals up here, and then you've got your intervals going down here as well. So this first one, sign of constant factor. So we don't have a constant factor. That would be right here. So since we don't have one, it is implied to be a positive 1. So it's all positive. Oops. Come back. All right, so sign of x. So that's just right there. So if x is less than negative 4, what is it? It's going to be a negative. That's where they got that. If x is in between negative 4 and 0, still going to be negative. If x is in between 0 and 2, it's going to be positive. And then if x is greater than 2, still going to be positive. Okay, so we're going down. So now we have the sign of x plus 4. So if x is less than negative 4, so let's say negative 5, what sign would this be? It would be, as they put, negative. So if it was negative 4 to 0, and I'm just kind of picking values, let's try negative 3. We could shove negative 3 into here, and that's going to be negative 3 plus 4. That's going to be positive. And then everything else is going to be positive as well. The lights went out. Let me see if I can't get them to come back on. Whatever. So the rest of these are all going to be positive because x is just getting bigger and bigger. So let's get rid of all of my doodle marks. And we're going to do the same thing. So sine of x minus 2. So if x is less than negative 4, so like negative 5. Negative 5 minus 2 is going to be negative. Negative 4 to 0. Again, let's try negative 1. Why not? Negative 1 minus negative 2 is still negative. 0 to 2. So let's try 1. 1 minus 2 is still negative 1. So that's going to be a negative. And then if it's greater than 2, so like 10, 10 minus 2 is a positive number. So that is where they got all of those signs. Once they get all those signs, then they're just going to essentially multiply them all together for your final positive or negative sign. And this is the same as multiplication. So you can even put ones in there if you wanted to. So like, positive 1 times negative 1 times negative 1 times negative 1, 3 negative ones, it's still going to be negative. So that means that if we were to start graphing this, let's see here. So we've got negative 4 over here. So it's below the x-axis. Let's get all of mine on there. Negative 4, 0, 2, and that's it. Okay. So it's going to be negative on this side. And we also know that the end behavior as x approaches negative infinity goes down. So, okay, that makes sense. So then from negative 4 to 0, again, they just multiplied all of these together. They got a positive. So then at 0, 0, notice we're going back to negative again. So I know it's going to go down, so it's going to cross. And then it's positive, so it's going to go up. So that is something like what our graph is going to look like. Now, of course, I'm sure that we'll have an example like this later on, but if this was positive here and then this one was positive as well, then we would have a tangent as opposed to a crossing of the x-axis. All right, let's see what they got for us. So how can you verify the results of the second column of the table? So I'm assuming they're talking about x is less than 4. Well, you can always just shove in an x to the original function and see what number you get. So you could theoretically, well, more than theoretically, but you can practically, type in or figure out f of negative 5, make sure it comes up negative. That would be one way to verify your results. So here's a pictorial number line of what we kind of already talked about. Infinity, it's going to be less than 0, then it gets positive, then it's less than 0 for a while, and then it's going to get positive again. How does the number line relate to the graph of f of x? Again, we kind of already went through it. Positive, negative. So, plot the intercepts. Did that. Use the sine table and the number line to help sketch a rough curve. For this purpose, you do not need to be precise about your y-coordinates of the points on the graph. Even a rough sketch reveals many key features, things like that. So, these two graphs are both correct. So you'll notice that they share similar qualities. It's negative down here, turns positive, negative, and then positive. So you'll notice that the graph that we made does the same thing. It's negative, then it turns, whoops, that's not what I wanted to do. Come back, numbers. There you go. So then it's positive up here, then it turns negative, then it goes positive again. Too easy, right? Too easy. You know what? We should try another one. Let's do it. I knew it. You wanted to do another one. So let's go. So sketch the graph of a polynomial function in intercept form. So here's our graph. I'm going to write it up in the corner so we don't forget it. F of x equals a negative, x plus 2, x plus 1 squared, interesting, x minus 1. Okay, so we're going to go through the exact same steps as before, but this one will be slightly different. So identify the end behavior of the graph. So we'll notice this time we have a factor here. So there's a negative 1 in front of our function. So again, the 1 is implied because we have a negative there. Cool. And on top of that, we have a degree of 4. So there's 1x, 2x, 3x, because it's squared, 4x. So, as I'm sure that you remember, our parent function of x to the 4th is going to look something like, we don't even need that. Is going to look something like this. So there's our parent function. But this one has a negative sign in front of it, so it's going to be flipped around the x-axis. So we put a negative sign in front of this one. Oh man, my handwriting's terrible. So if we have a negative x cubed, it's going to look something like this. So from that, we can look at it and figure out as x approaches negative infinity, f of x goes to negative infinity. As x approaches positive infinity, f of x goes to negative infinity. So that's all that part, all that part. Right? Too easy. No problem. Okay, got that part. Moving right along. Let's get rid of some of my little doodles here. So how does the negative leading coefficient of f of x affect the end behavior? It reverses it, or I guess it makes it the opposite sign, whatever words they want to use. So identify the graph's x-intercepts, use them to define the intervals, create a table, and do all that fun stuff. So here, I'm going to skip a couple of steps. Hopefully you can follow along, but I can see that we have an x-intercept. Let's make this work. X-intercept at -2, -1, and 1. So that's when this guy equals 0, when this guy equals 0, when this guy equals 0. Okay? Cool. So that's also what they got. So that's good to know. How do you identify the x-intercepts? You set each factor equal to 0, and then you solve for x. So they have our chart set up. So again, we have our interval from -infinity to -2. Come on, pen. There you are. -2 to -1, -1 to 1, and then greater than 1. So those are going to be our things we're working with. So our sign of a constant factor, so our constant factor here is -1, so they're going to do negatives all the way across. Okay, done. That's the easy part. So sign of, and again, down here it's all of the factors. We can get my face out of the way. No, I like to peek at you. All right, so again, as I was saying, so we've got our sign of our constant factor, and these are just our factors going down the line. X plus 2, which is our first one, x plus 1 squared, x minus 1. Okay, cool. Let's make it happen. So sine of x plus 2. So if x is less than negative 2, so let's say negative 3, sine of x plus 2, that would be negative 1, so it would be a negative sign. Okay? Negative 2 to negative 1. So, I don't know, negative 2.5. Sure, why not? So it is going to be negative, not 2.5. I'm sorry, that's wrong. Negative 1.5. I forgot we're on the negative side. So negative 1.5. So that's gonna, if we plug that into there, that's still going to be positive. So then, and then negative 1 to 1. I'm going to pick 0 because why not? X equals 0. So then the sign of that's going to be positive. And then greater than 1, it's going to be positive again. Okay, this next one's easy. X plus 1 squared. Hey, fun fact. If we get a negative sign inside of here and then square it, what is the sign going to be? Positives all across the board. Done. Too easy. So then sine of x minus 1. So if x is less than 2, again, negative 3. So that's going to be negative. Negative 2 to negative 1. I don't know, negative 1.5. So negative 1.5 minus 1 is going to be negative. So that's where that one came from. Negative 1 to 1, we're going to use 0. 0 minus 1 is a negative number. And then anything greater than 1, if we plug into there, will in fact be positive. So then we take all of these signs, multiply them together. And now we should be able to sketch the graph. So let's say I'm going to do it over here. Okay, so I've got negative 2, negative 1, and 1. And we'll sketch in green, because why not? So from negative 2 on, it's going to be negative. And then it switches to positive. And notice how it's positive and then positive. So that means, so we're coming up, then back down, but we're not crossing this time because we're still positive. And then we end negative. So it's going to look something like that. Of course, I made my little bump here way bigger than they did. But again, at this point, with the information that we have or that we can use, they are both correct. So let's get rid of some of my doodles. Goodbye, doodles. So is f of x positive over the entire interval negative 2 to 1? That is right there. We can say yes, because it's all above x. And then, let's get rid of that. So let's see what they're looking for. Yes, there is an x-intercept of -1. So f of x is positive at 0. Maybe? Ugh. Okay, fine. So what they're talking about these zeros, I bet. Because there's an x-intercept at -1, so f of x is positive at x equals 0. Is that better? I knew you wanted to do one more, right? Let's do it. All right, so here we go. Analyze graphs of polynomial functions. This is our last task. So we're going to model using a polynomial function. They're used in many real-world applications, especially cubic polynomial functions when dealing with volume. So here we go. Sheena is creating an open-top box from a piece of cardboard. She forms a square flap of the side length x at each corner by making a single cut, a solid line cut, and then folding on the dashed line to form the flap. She then folds up the 4 sides of the box and glues each flap to the side it overlaps. What volume of x to the nearest tenth maximizes the box's volume? So we need to find the volume of a box. So the volume of a box, again, I'm sure everyone remembers this, is, come on, length times width times height equals volume of a box. Okay, so our length in this case is this part, which is that 11 inches? No, it's not. It is 11 inches minus that piece and that piece, which we know is x. So our length is going to be 11 minus x. Okay, so our width is going to be, is going to be this part right here, which is not 8 inches. It is 8 inches minus, is it 1x? There's an x here. There's an x here. So it is actually 2x. Which, of course, that means I got my other one wrong, too. So let's fix that. So that's 11 minus 2x. And then we have times 8 minus 2x. And then what is our height going to be? So think about that. So if we're folding things up, like the diagram shows, this little piece right here, this whole thing would be being folded up, and that would be our height. So how high is this part right here? You guessed it. That would just be x. And I put an extra parenthesis there just for fun. So now we have a third degree polynomial that we know how to work with, right? So for this one, since we are trying to find the maximum volume, at this point is where you pull out your graphing calculator. So we don't have the mechanisms yet to find maxes and minimums. I think that's kind of a calculus problem. But we do have graphing calculators. So this part here just goes over how they formed their equation. And we're going to get my doodle out of the way. So again, here's their equation. Looks like ours. What assumption is the volume model making about the thickness of the cardboard? Well, it's not a good physics problem unless you assume, I don't know, something that makes it unrealistic. So at this point, we're assuming the thickness of the cardboard is infinitesimally small. So we're just not dealing with the thickness of the cardboard. That would, again, just add another complication into this problem. So the box's dimensions must all be positive, which makes sense. You can't have a negative length, which gives the domain restrictions. Again, they just need to be positive. So x's all have to be positives. And then at this point is when you pull out your graphing calculator, and then you'll have something that looks like this, and you can use your graphing calculator to find the maximum value right there. So let's see, the maximum value of about 60.0 occurs when x is approximately 1.53. So take a minute and actually make sure you know how to graph on your graphing calculator. It's going to be useful at this point. And then with that, you know your x, and then you can solve for your volume, and ta-da, you have solved the problem. Good job. Now at this point, I want you to try it yourself. Try the check on learning, and I'll see you in class. Bye.